So we're going to go ahead and start with building reactions, and these are the types of questions you can kind of start expect from me, because these require you to do kind of all the things right at once. These are complex kind of problems. A little bit high stakes, because you have to make sure you get the equations built right, and then you get it balanced right, and then you do the stoichiometry right. So these are a little bit more high stakes, but let's just look at it and see what we see, okay? First of all, double displacement reactions. We didn't talk specifically about what a double displacement reaction is. We talked about balancing reactions, but we didn't dive much into types of reactions. So let me jog your memory here. A double displacement reaction is when we see molecules switch basically partners, right? A double displacement reaction is when cations and anions switch places, okay? So when we build a formula, it's a cation and an anion, and then another formula, cation and an anion, right? Different, whatever these things are, it doesn't matter. Some cation A is paired with some anion B, cation, anion, right? So when we form a double displacement reaction, we see the cation from the first and the anion from the second join and become a new compound, and we see the cation from the second and the anion from the first join and become a new compound. Right? So we go new compound AD plus new compound CB. Right? And why does this compound have to be written CB instead of BC? Right? Why is it that way? The cation has to come first. Whenever we build a formula, the cation has to go first. So in these formulas, plus, minus, right? Whenever we build a chemical formula, it's got to be cation, then anion. And so when we build our finals, it's still got to be cation first, then anion. Okay, so that's how a double displacement reaction works. The cation and the anion trade places. So let's go ahead and build one here. This says potassium nitrate reacts with magnesium fluoride to create something. Okay, so let's go ahead and build that. I'm going to give me some space up here at the top. All right, first of all, we got to get our formulas right. Potassium nitrate is KNO3. Agreed? Okay, and magnesium fluoride is it just MgF? Sorry, get out your periodic table of ions if you don't have that out yet. Okay, you're going to need that today. It would be MgF2 because magnesium is a +2, fluoride is a -1. Okay, so when they come together, it's got to be MgF2. So now those are our reactants. We have to guess what our products would be. Yeah?
Why would it be MgF4? How do you know if it's 2 or 4?
We're talking about magnesium, not manganese.
Oh.
Magnesium is Mg, so it's in group 2.
Oh, okay.
It's a little different. That's okay. All right, so now we predict our products. Potassium is going to bond with what? Fluorine, right? And so does it automatically go KF2 like it was here? No. We have to pay attention to potassium is +1, fluoride is -1, so we go just KF, right? That's super important. You will balance the atoms later, right? When you balance the reaction, you'll balance that part of it later. So just build the formulas correctly right now. Second product would be magnesium, right? The insides come together, magnesium nitrate. So that would be MgNO3, 2. Good, right? Don't forget parentheses there. Okay, so now we've built it correctly, right? We think all of our formulas are correct. And then we have to balance it. Okay? If I'm going to balance it, I'm going to look for like obvious fixes first. Right? You can make your list if you want, but as we go through this class and we do it more and more, you're going to be able to recognize those things earlier. So the first thing I see is fluorine, right? I need to add a 2 here. And so what does that force me to adjust then? The potassium, right? I have to look at potassium and see, okay, do I have 2 potassiums? No, I don't. So I add a 2. Okay, so then what else does that force me to adjust? Nitrate. So I go look over here. Do I have 2 nitrates already over here? Yes, and then I just check last. Magnesium is good on both sides. Okay, so you can do it without the list. You just bounce back and forth, right? But it'll take some practice for you to feel comfortable doing it that way. If you're not comfortable, just make your list, okay? All right, so now I can actually start answering the question. If 112.42 grams of potassium nitrate, if I start with that much, how many grams of magnesium nitrate will be produced? Okay? So let me go up here, and I want to write up here what I'm kind of focusing on. I start with yeah, that's right. If this was one problem on a test, right, this would be a big one. Okay, if I start with 112.42 grams of potassium nitrate, how many grams of magnesium nitrate will be formed, right? The reason I write it by my balanced equation, it kind of makes me zone in on what my mole ratio needs to be, right? It makes me like kind of pay attention to, these are the two compounds I'm working with. All right, so when I go to start my T-chart now, I always start with what I know. 112.42 grams of KNO3. Go ahead and grab calculator out if you don't have that, right? Because we need that to calculate molar mass. In this problem, I was asked for grams of a starting amount and then grams of my product. So will I ever use Avogadro's number? No, right? I don't ever need to put it in there, so don't bother, right? I'm going to go grams of KNO3 to moles of KNO3. Anyone have that molar mass? 101, thank you. Okay, from there, I'm going to get rid of moles of KNO3 and go to what?
Moles of MgO3.
Good. MgNO3 too, right? What's that part of my chart called right here?
Molar ratio.
The mole ratio, right? That's the only part that I can ever have two different substances in the same column of my T-chart, right, is in that mole ratio step. And where do these numbers come from? The coefficients, right? The balance formula. So potassium nitrate gets a 2, magnesium nitrate gets a 1. And then I'm going to come down, final step, moles of MgNO3, 2 grams. 148. Are we good with that molar mass? I didn't actually calculate it, but I'm going to trust. We should have something.
No.
Magnesium can't be a whole number. We need to take it to at least a 0.3 there. So it might be 148.3, but
Oh, yeah.
does that make sense? Okay.
Sorry, I didn't see that.
That's okay.
0.3.
That's all right.
Is that wrong?
148.3 grams. So now we multiply across the whole top, divide by the whole bottom, and we get 82.5, or no?
Yeah.
Okay.
82.53.
That's what I got. Right, I don't punch things back into my calculator, right? Everyone here use the answer button and use that function. Let's talk through, what does the word yield mean?
Slow down. Look out.
Okay, not pedestrian yield, chemistry yield.
Like if the smallest amount falls to the dozen?
No, okay, I think I don't know. Produce is what we're thinking. Yield means to produce, right? What is my yield? How much am I producing, right? That's what it means. So when we calculate percent yield, we're going to look at the comparison and what was supposed to happen versus what actually happened, right? That's the goal. Did we do this at all in Chem 1? Did we do percent yield last year? Yeah. We did a little bit at the end. Okay. I don't remember if we covered that in our remote part or not. So percent yield is basically looking at what we should have gotten and what we actually got when we did it in the lab, okay? So what we've been calculating so far is theoretical yield. It is theoretical because it comes from our T-chart, okay? That's a big clue. The fact that it comes from our T-chart means it's a calculation. It's theoretical, right? This is what we were supposed to get. So in that last problem, starting with 112 grams of lithium phosphate, we should have produced 82.5 grams of magnesium nitrate or magnesium, whatever it was. But it doesn't mean when we go into the lab and do it, it's actually going to happen that way. Okay? So our equation for percent yield is this. We take the actual yield over the theoretical yield. Actual yield over the theoretical yield. Okay, actual over theoretical, you're going to end up multiplying it by 100 to get it back into a percent. But you're going to take your actual divided by your theoretical to get percent yield. This would be a question you'd answer like after you've done your T-chart, right? You've solved for what should have happened, and then it would say, what happens if your yield is only 80% or whatever, blah, 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 right? We're going to look at what that looks like. But there's our equation for percent yield. Percent equals actual over theoretical. All right. So now we're going to do the chart. We're going to do the actual stoichiometry problem, and then we'll say, what's our percent yield if only 7.95 grams are formed? It's already balanced for you. We're going to just go with the chart here. Okay. So let's see, 36.5 grams of O2. We're going to cancel grams of O2 and go to moles. 1 mole is 32 grams. From there, what's my next step? Good, mole ratio. Moles of O2 to moles of water, H2O. And those come directly from our coefficients in our balanced equation. So oxygen gets a 6 and water gets a 3.
Do you simplify that?
Yeah, you can, but I don't waste the time doing that. Because it just goes all into your calculator anyway. So there's no difference between plugging in 3 and 6 and punching a 1 and a 2. You know what I'm saying? So then we'll go moles of water to grams of water. Right, down here, would this mole ever get the 3? Since there's a 3 right there? No, because the grams is how many grams is in 1 mole of it. You have to really be careful with that. All right, then we punch it into our calculator. 36.5 times 3 times 18, divide by 32, divide by 6. And we get 10.26 or 10.3 grams, right? Not concerned with significant figures here. That's not going to be something I'm really looking at. Okay, 10.3 grams of water. So is this our theoretical or our actual yield?
Theoretical.
This is our theoretical because it comes from the T chart, right? I'm really trying to give you a clue there. T theoretical, T chart. Okay. So now it tells me that I did the experiment and only 7.95 grams were formed. So I plug that in my percent yield equation and I say 7.95 divided by 10.3 gives me a 77.4% yield.
Yes. Look at us.
Okay. Do this whole problem, but let's say that we have a percent yield. How many grams will be produced? This would mean you would take your theoretical that you get from your T chart. Right? You would do the T chart, you'd get your theoretical yield, and you would say 0.39 equals A over whatever my theoretical is that I solved for my T chart.
Wow.
Okay, so if we did this whole problem and we actually solved out,
So that'd be just 0.39 times it.
right, you would just take your theoretical from your T chart, multiply by 0.39. The only important thing you have to realize there is that this 39% has to be converted to a decimal. Right, and then we look for our actual there. Okay? I don't need us to actually do that problem if we feel pretty good about it. Okay, let's go to limiting reactant because this is going to be the bulk of what we wanted to do today. When I say the word limiting reactant, are you processing what that means?
It only has a certain amount.
Yeah, good. One of my reactants is going to limit my production, right? When I put two things together, they're going to react. Molecules are going to bond, right? We're going to do all these things until one of them runs out and they can't do any more bonding, right? Does that make sense? So when that happens, the reactant that runs out first is called our limiting reactant, okay? Wow, I really went a little simpler than I thought I would. Okay. Basically, I need you to think about chemical reactions like a recipe, right? In Chem 1, I break this down way, way further. But we think about a recipe. Like if I need to make a recipe with 6 cups of flour and I only have 4, can I make the whole recipe?
No.
No. I have to adjust the recipe. Or I make as much as I can with only 4 cups of flour, right? But what my flour would be my limiting ingredient there, or limiting reactant, right? I don't have enough of it, so it limits the amount that I can produce. Okay. So we think about a balanced chemical reaction as a recipe for our experiment or a recipe for our reaction. Usually we can predict the amount of product that's formed, but when we have a limiting reactant, there's 2 different amounts that we can form, right? The amount from each of our reactants, and then we have to see which one produces a smaller amount. That reactant would be my limiting one. Okay, so we'll look at that in just a second. Okay, take a look at this, this balanced formula. 1 mole of nitrogen gas plus 3 moles of hydrogen gas yields 2 moles of ammonia, right? That's the formula. So now let's look down here. How much NH3 could be formed if 2 moles of N2 were reacted with 3 moles of H2? How much product can I form?
4 moles.
2 moles.
How many of you think I could form 4 moles of my product?
I don't even know.
How many of you think I can only form 2 moles of my product? That's right. I can only form 2 moles because this is exactly how much I'm supposed to have. Right? This is double what I'm supposed to have. So this doesn't matter if I have extra. I have exactly how much I need of hydrogen gas, so that means I can only produce 2 moles. Does that kind of make sense? We're not going to see many problems like this that are nice, pretty, whole, round numbers that show it this way, right? We're going to have to actually do the math to figure out which one's going to be limiting. But in this case, H2 is what I would consider my limiting reactant, right? I'm going to have excess, that's what word we use, excess of N2, right? There's going to be extra N2 left over. Does that make sense? Why that? Do you see that? Yeah, give me like a yes or no. I can't really read what you guys are thinking.
So the equation is correct.
The balanced equation is exactly right. So we're saying if I start with 2 moles, like let's say I'm going to do the experiment. I have 2 moles of N2 and 3 of H2. I'm going to use up all 3 moles reacting with only 1 mole of N2, and I'm going to have a mole of N2 that's left over.
This is kind of what we finished on.
Okay,
Chem 1.
good.
Soft.
This is how limiting reactant problems will look. You will be given starting amounts for both of your reactants. You're going to be given, I'm starting with 82 grams of copper, and I'm starting with 25 grams of sulfur. And the question asks, what is the maximum amount of my product that can be formed? So in order to answer that question, we have to figure out first which is the limiting reactant. Which one is going to run out and stop our production? Okay? The way you do that is you have to solve a T-chart for both. Yeah, this is where we get like into T-chart city. Okay, we have to do a lot of them here. Okay? So let's just dive in. All right, 82 grams of copper is my starting amount. I go grams of copper to moles of copper. Moles of copper to moles of sulfur. Nope. Moles of copper sulfide. All right, we're going to go to our product because you want to know what's the maximum amount of our product that can be formed. Then we'll go moles of copper sulfide to...
whichever has the bigger number.
Whichever has, well, yeah, so we'll talk about that in a second, but yes, that's what we're going to compare. All right, molar mass of copper, I think, is 55.85. Yeah, or no?
63.5.
Sorry. Okay, what am I doing, iron? 63.5. 55.85 is copper. Oh, no, I mean, it's iron,
Iron, yeah, 55.8.
Okay. All right, so moles of copper here, we're going to go 2 to 1. Then we go 1 to, I don't want to calculate that molar mass. So whoever has it done, I'm going to believe you.
Copper times 2 plus sulfur.
159.
Yes. 159?
Yeah.
Okay.
I got 165.
Oh.
Am I wrong?
63.5 times 2 plus 32 is 159.
So,
That's okay. Okay. So go ahead and multiply across the whole top, divide by the whole bottom. and we get 102.66 grams, right?
Yep.
102.66 grams of Cu2S. You want to be really careful here of labeling all of your answers because we're going to start dealing with a bunch of different compounds, right? You're going to do the problem with a bunch of T-charts, and you need to be really, really crystal clear about which one you're dealing with. Okay, so that's how much we can produce. Let's stop what you're doing and listen for just a second because this is the concept of it that people kind of seem to miss. This is how much we could produce if we used up all 82 grams of copper, right? If all 82 grams is used in the reaction, we could produce 102.66 grams, okay? Just leave that in the back for a second, and let's do our other T-chart with sulfur, right? 25 grams of sulfur, 32 grams is to 1 mole of sulfur. Moles of sulfur to moles of copper sulfide. This is 1 to 1. And then moles.
What? Huh? Oh. Silly.
All right. So we multiply across the whole top, divide by the whole bottom.
124.
Okay. 124.22 grams of Cu2S. Okay. So here is our two values. The top one says if we use up all 82 grams of copper, we can produce 102 grams. If we use up all 25 grams of sulfur, we could produce 124 grams. So which of these has to be my reactant that is limiting my production? Copper. Exactly. We look at which one gives us the smaller amount of product. That points us back to our limiting reactant. We can't just do this and say this is our limiting reactant. Right? That's not the case. This is answering the question of how much copper sulfide can be formed. But my limiting reactant is copper. We go back to my starting amount and I say my limiting reactant equals copper. Right? Because it's going to be used up first. Right? All 82 grams of it are going to be used up, and there's going to be some sulfur that is left over. Okay, eventually we'll look at how we calculate how much sulfur is left over. But for right now, we look at sulfur is in excess. So sometimes the questions, we've had a couple questions previously that say this reacts and whatever compound is in excess. That's all it's saying is that you're not in their limiting reactant. Okay? Any questions about that one? Smaller amount of product points us back to our limiting reactant. All right. Why don't you want to try this one on your own?
No, sure.
Why don't you get started? I'll give you like a 2-minute head start.
So do we not round magnesium?
No, it needs to be 24.3.
Okay. Are we allowed to round chlorine to 35.5?
Yes.
So you just do the math.
So in this problem, there are two products, right? There's two products. And this question does not ask us anything about one specific product, correct?
Yeah.
It just says, what's the limiting reactant?
So we just find one.
So you get to pick which product you go to, but you need to go to the same product in both T-charts.
Yeah.
Does that make sense? I would pick the one with the easier molar mass, so hydrogen, right? That way I don't mess that up. Does that make sense?
Yeah.
So this problem doesn't specifically ask you about a specific product, so you can pick which product you go to. So I would go to hydrogen because its molar mass is easier to calculate. But you need to go to it in both T-charts because we want to compare grams of hydrogen and grams of hydrogen. Does that make sense? Like I'm going to make a T-chart from HCl to H2 and then from Mg to H2.
Oh, shoot.
Right? But I'm not going to go HCl to H2 and Mg to MgCl2 because then I won't have anything to compare. Right? I want to compare apples to apples. I'm not going to ask you to do this, but what if it said, what's the maximum amount of each product that could be formed? If it asked for the maximum amount of each product, I would say, here's my maximum amount of H2, And then I would have to do another chart that goes from HCl to
magnesium.
perfect, right? I would do another chart that would go from HCl to my other product. Would I need to bother going from magnesium to my other product? No, because I know that HCl is my limiting reactant. So once you know what your limiting reactant is, every chart you do should start with that. Okay, do you want me to say that again? Once you know what your limiting reactant is, every chart should start with that. Okay, feeling good? You're going to get through what's the limiting reactant and what's the maximum amount of iron oxide that can be formed, right? You're going to get through that part on your own, and then I will help us answer the last question here, okay? This one, oh, it only has one product, so it doesn't matter. I don't think it's balanced. You need to balance this. Balance it first. And then you're going to get through this. I will help you with the very last question there, so go ahead and start. Are those the numbers we got out of ours? 64.3 grams and 288.2? Or no? 289.2 in the ballpark, okay?
289. Yeah, I got 289.
Okay. It must have just been a calculator thing for me, but okay.
I did 9 grams for the.
Oh, I didn't put 0.7, you're right. That's why.
159.6.
Yep, that's my
Sorry,
fault.
too.
When I was writing it here, I had it zoomed in and I didn't see that 0.7. Yep. Okay, so we should be 288 or 289 right down here. Sorry about that. Okay. If you didn't quite get that, do you see an area of the T-chart that doesn't match? Okay, so the first question we can answer, what's the max amount of iron oxide that can be formed? What is my response there? 64. Okay, good. It's very, very simple to say, oh, this number is bigger, so that's the maximum amount. No, right? This is going to run out. Iron is going to run out before we can produce that much. It's going to run out after 64 grams. Okay, now the question is, how much excess reactant is left over? So that means we want to see how much oxygen gas is going to be used up in the reaction and then left over. Okay, so here's how we do it. We look for a T-chart that goes from our limiting reactant. So I'm going to get rid of this bottom one down here. We're going to go from our limiting reactant to our other reactant. Okay, and this one would tell us how much oxygen gas is used, right? This one's going to tell us how much we use, and then you subtract, right? So we're going to say we're going to go from 45 grams of iron Okay, and so what this T-chart tells us, and this is super important, it tells us how much is used, right? It's saying if we react all 45 grams in these ratios, this is how much oxygen is used. Okay, so if I go 45 times 3 times 32, 55.85. So that gives me 19.34 grams, I think. This is used. Okay, so that's not what the question asked for. It asked how much was excess or how much is left over. So now we know if we use 19.34, but we started with 87, we're going to do 87 minus 19.34. And we get 67.66 grams of O2 left over.